Hello, I'm Gabriel Bliard, and I will be speaking to you today about Witten diagrams and analytic bootstrap for the ABJM half BPS Wilson line. So this is a project that was in collaboration with Lorenzo Bianchi, who will be speaking also at Cortona Young, Valentina Forini, Luca Griguolo, and Domenico Seminara. The preprint is on the archive if you want to read a bit further. So a few caveats for this talk. One of them is that I haven't actually done a remote video poster before, so I hope you'll be a bit patient with me, and I'll be around during the actual day if you want to ask some questions. The second is this is going to be quite short, so I hope I give you a bit of an overview of things, and as always, I'm happy to talk about details later on. All right, so this is going to be focused a lot around dualities. So I'm going to present the system and the duality and try to motivate a bit what we did. So the system we're looking at is in particular n equals 6 Chern-Simons with matter, ABJM theory, and its dual type 2A and ADS4CP3. The actual system that we'll be looking is actually a subsector of this, which will be the minimal string surface in the ADS4 cross CP3, whose boundary will be ending on the half BPS Wilson line in the ABJM theory. So here on the bottom left, you can see the worldsheet picture, which we're going to use again for Witten diagrams and such. And on the right-hand side, you can see the Wilson line, which is in the time-like direction, indicated as 0. So within this, we'll be interested in a certain class of operators, which are going to be operator insertions on the CFT side. So I won't go into a lot of detail because I think Lorenzo Bianchi will probably detail all of these, but these are going to be the operators that we're going to look at through the correlators, and these are dual to the fluctuations on the ADS side. So the fluctuations of the actual string worldsheet at the boundary in the directions orthogonal to the worldsheet. So on one side, we're going to compute these correlators perturbatively using Witten diagrams, which are the ADS equivalent of Feynman diagrams. And on the CFT side, we'll try to relate these correlators. And these can be computed, and they have, through Bootstrap at large coupling, which is going to be what we'll be interested in. Notice that they can also be computed at small coupling through perturbation theory. So why do we care about these objects? The correlators are particularly important because they actually define your defect field theory, where your fields will be your operator insertions, and your objects will be the correlators on your Wilson line. So you'll have a well-defined CFT1. Furthermore, your defects are actually fundamental non-local observables of a theory. So without them, you don't have a complete description of your theory. Finally, the actual Wilson line and deformations thereof through these operator insertions give you something that's quite physical. A very well-known example relates the two-point function of the displacement operator inserted on the Wilson line to the Bremsstrahlung function through the in the famous paper of 2012, radiation of a moving quark. Also, we're quite interested in completing this ADS CFT dictionary. So these next examples will be a good context for an interesting context in which we talk about ADS2 CFT1. it's also interesting to look at these problems because you can apply a lot of CFT techniques, analytic techniques that work quite well in this system. Finally, this is a theory that's simpler than full ABGM, so we actually have some hope of solving some sectors of it exactly. So I'm going to start by presenting what we've actually computed. So in the defect CFT, the correlators organize themselves very well in a form of a multiplet. So these have a nice super multiplet structures in which the different components are related through transformations under the supercharge Q. And we'll be looking at these components of the super multiplet inserted in on the Wilson line, forming these correlators. So one of the very nice consequences of these having a super multiplet structure is that we can apply the full power of superspace. So these actually are more than just a super multiplet. They're chiral super multiplet, so we can write it in the form given with the first equation with a chiral superfield phi. We can then define a chiral to antichiral distance, and we then can form the single supercross ratio bold chi. From this, it means that we can fix all of our 2-point functions, which are just going to be a function of that distance, and 4-point functions, which are going to be a function of that cross ratio. And from this single function, we can deduce all of the component correlators. So this is the system that we're looking at. So for the concrete calculations, I'll be presenting the ones that we did on the worldsheet side, on the ADS side. So we use a gauged fixed action that's expanded around the minimal surface. So this is the usual Nambu-Goto action, and where x bar, w, and w bar are the remaining ADS4 and CP3 directions. We then expand this around small values of x and w, so that we find an action that's effectively that of propagating fields on an ADS2 space. The x's have mass squared 2, and the w's are massless. Through this and the other quantum numbers, we can identify them very easily to the CFT fields through the ADS CFT dictionary. Once we've done this relation, we can actually use this superspace formalism to relate the correlators that we can compute through the equivalent of Feynman diagrams in the ADS picture to the differential expression in terms of this superfunction h, and actually solve for this superfunction h, which determines all of the 4-point correlators up to this order in perturbation theory. So this is the superfunction that we've been looking for, h, and from it you can find all the correlators. This was then confirmed by bootstrap analysis, constraining the possible forms of h through symmetries, and we found the agreement of these two models. So in further projects, it'll probably be interesting to look at Witten diagrams with loops to confirm that we have in this case also the agreement of the Bremsstrahlung function, of the normalization of the 2-point function. It'll also be interesting to look at bootstrap at higher order to see if we can actually find order by order these correlators. Recently, some examples of integrability have been discussed in the context of n equals 4 super Yang mills. It would be interesting to look at the same thing in this case. Finally, finding topological sectors would be quite interesting, as there weren't any in this case, because that would allow us to compute the correlators exactly through localization, and we could also apply this to other CFT defects. Anyway, I hope you enjoyed this. I'll be around later if you want to speak to me about this. And thank you for your time.